honor speaker, Dr. David Hooper, who's at Oak Ridge National Lab, and he is the group leader of the Incident Modeling and Computational Sciences group in the Nuclear Nonproliferation Division. And I'm pretty excited to have David here. We've been collaborating for many years on looking at health effects of nuclear debris, but what's actually more interesting to me is to hear about this. It's probably a rare opportunity you'll have to hear about this topic in an open setting. So we're going to be hearing about nuclear detonations. So.
Thank you. Yeah, it's pretty much me in a nutshell. I'll get into it. I didn't realize it was a 50-minute hour, not a 60-minute hour, so we'll see how this goes. There we go. Okay, so I'm going to just quickly describe our group, give you kind of a context of who we are, what we do. Obviously, it's nuclear non-proliferation space, nuclear security safeguards, all that. But our group is a bunch of basically computational scientists, software developers, modelers. We build software for, as you see on the slide there, nuclear forensics, consequence management, focused mostly on the debris aspect of, say, a post-weapon detonation, reactor accidents of some form. War in Ukraine is keeping us quite busy right now if you want to think about that kind of context for the reactors or facility safeguards. That's kind of like the 30-second version. A few of the projects I'll just kind of highlight real quick to give you a little bit more flavor. This is one of our NA-22, which is one of our nuclear forensic ventures that we work with a bunch of the other national labs on. And going from the detonation picture upward, we build some higher fidelity models of the actual nucleation formation of the debris out of the fireball, alongside its transport all the way through the consequence management and forensics activities, all the way through the diagnostics and the forensics that they do on the back end of the lab. So the kind of whole end chain of modeling of the debris topics. On the bottom end is some of our machine learning ventures. You can't really see from back there. There's a bunch of little green and red dots in there for feature tracing inside the rising fireball. So as you get a video of it moving up, you can do some yield estimation, estimates on the vorticity and the entrainment of the air inside of it, which affects the chemistry. On the again, on the software development side, we do a lot of software development tools for if a nuclear weapon went off in the United States. There's going to be a whole lot of activity going on, obviously, the consequence management, getting people safe. There's also going to be a forensic side involved where they do some debris collections and analysis, couple that with the acoustic signals, the seismic signals, the light signals that come off with the explosion. To kind of backtrace what happened, what kind of a device it was, where was it, how effective was it, and so on. They're going to do all that kind of forensic analysis. And that's actually led, I don't know if it's on this slide here. No, it's actually led by the FBI. It's treated like a crime scene investigation, so there's a whole continuity of evidence that has to go alongside of it. And so they do training and exercises to follow that. So we build them tools to plan their missions. They go to the collections, then we have some other tools that simulate those collections. They tell their controller, okay, we collected X amount. They do some mumbo jumbo in the background, come up with what the samples look like, and they can run through the entire process and keep the data consistent step to step. That's kind of our post-detonation side. For Department of Defense facility accident modeling, we have some in-water explosion model. We do some nuclear fuel cycle analysis, everything from mining all the way down to the deep repositories. Modeling a cycle, looking for consistencies. This is really useful for safeguards declarations, for example. Is somebody operating the way they say they're operating? Is it consistent? Does it make physical sense what they're declaring? And then two projects that a few of you here in the room know pretty well, one at the NIH, one at the NIAID. This is the work that Northwestern, Georgia Tech, Berkeley, and Florida are doing to look at internal dosimetry and measures to mitigate that. And I and some associates over at ORNL just serve as subject matter experts. The universities do all the actual research. We just provide the knowledge we've obtained to kind of help and support and make sure, like for me, I make sure that the debris that's being modeled in their research is consistent with what we've seen in the past. So that's kind of what our group does in a nutshell. That's kind of where I'm coming from. The project I'm going to talk about is one that ended a couple of years ago. I thought this one might be interesting. It was one of the most fun projects I've ever worked on. where we coupled with some of the people out of our quantum information sciences side of the house at the lab, and looked at if you have communication channels between ground stations and satellites, and a nuclear explosion goes off, what kind of disturbance does that cause in that channel? How persistent is it? How severe is it? Under different conditions, what are the different types of insults you might receive? This was born out of two different kind of events. One was in the mid-2010s where North Korea was still doing their testing, and the threat of another state actor who might actually use a weapon seemed to be a little bit more real at the time. So the idea of weapons being a problem was a little higher. And then in the later 2010s, there was a lot of journal article publications out of China about sending a entangled photon from satellite down to a ground receiver and maintaining the entanglement at reception, which is absolutely huge in quantum key communications. If you can refine that process enough, you can send encryption keys through quantum entanglement, and it becomes practically unbreakable at that point, because if you try to read the key, you break the key. And so you cannot intercept the key and still have it as a functioning key. And so the two kind of aligned were looking at satellites as well as looking at nuclear detonations. Both had a lot of coupled relevance. And so that's what we're going to be getting into. And the ultimate goal, I'm going to explain this little graphic. Kind of self-explanatory, different possible effects. You can see the duration of those effects, but we're just going to kind of walk through each of these and kind of take you down the story of everything we looked at. So we'll start with the first one. We'll start there is that second one in the row, the debris side. So this is for near surface bursts where a nuclear explosion sucks up a lot of the dirt off the ground, and that becomes a part of the fireball itself. This is, in nuclear explosion, this is where you get fallout from, is if you're close to the ground. If the weapon's too high and it can't interact with the ground, the particle is so small that it takes so long for it to come out of the air that it's effectively what's known as quote-unquote fallout free. This was actually the case for Hiroshima and Nagasaki, except for the rainout, particularly in Nagasaki, that occurred where precipitation was caused by the explosion that ended up dragging the particulate down with the rain. And so you got the black rain being occurred out of that. So there's a little bit of, historically speaking, there's a little bit of discontinuity with the term fallout free, but we're going to look at the surface first. Okay, so again, the question, we're looking at communication to the ground. There's a few different channels. You can go straight to low Earth orbit LEO satellites, or even all the way up to higher. You can use airplanes as an intermediary. We did a look at some of these different channels. We're going to keep it basically satellite to LEO for this conversation. You'll get the picture. You can copy and paste for everything else. Things we're not going to look at, not direct blast damage, the thermal radiation effects, or fallout literally landing on the ground station. Those obviously take out the station. It's not very interesting for the research, so probably not the best use of our tax dollars if we were to spend a year telling you that a nuclear blast is going to take out a ground station. So we're not going to look at those. We're just going to look at, it goes boom, cloud goes in the air, debris goes transported downrange, downwind, and it goes in the line of that ground to satellite communication. How big of an effect is it? How persistent of an effect is it? How long do you have to worry about? Yes?
What agency has responsibility for EMP, which is stratospheric and above bursts? Is that also DITRA, or is it? I guess this is not part of your...
It's not. It's a good question. So for those high altitudes yet, DOD has some responsibility. DOE has some responsibility. I would imagine NASA has some. It depends on what problem it is exactly you're looking at. Certainly from the tactical sense, it's a DOD problem. The technical sense, it's a DOE question. Okay, so a little bit on attenuation of signals in the air, of EM signals. So bottom here, the frequency. On this left side is generally where your radar ranges are. X-band is about here. K-band is here. There's the reason there's a gap between K upper and K lower, the KU and KL bands. And then you can see the molecular absorption. You can see that the CO2 and H2O give you all these various little spikes. There's a couple of nice little points here over at 1550 and 800 nanometers in the optical range that you have pretty low attenuation rates in the atmosphere. So if you have a clear air atmosphere, it's about as reasonably low as you can get. So those tend to be two of the favorite channels for optical way of communication. And those are the two we ended up looking at for sending these entangled photons. And then you can't have a nuclear talk without a nuclear video, so I'm going to take a quick look at this, and I want to point out a few features. There's boom. Priscilla is one of the prettiest ones you'll see. I'll show you why in a second. Okay. Right there. Okay, so if you watch the cap, and you see this bright line in the middle of the cap, what happens, you get the fireball expand, and then because it's so hot, it's actually a much lower density than the air. Even once it expands, you'll see a pause in videos when they stop expanding. That's when pressure equilibrium is reached, but the density is lower. And so lower density, it's going to rise in the air. As it rises, the atmosphere acts as friction, and the atmosphere comes down around the outside, pulls the skin downward, which causes the internal to go upward. And then you get this toroidal vorticity on the inside. What that does is it kind of contains it, and you get that mushroom cloud effect that goes up, rather than just kind of, immediately dispersing everywhere. You get this kind of rising engine, if you will, that lofts itself up in the air. And you're seeing kind of that hot zone, that hot toroidal center in the shot, which you can see better in Priscilla than you can in the other. And you can see the motion around it, right? So that's what's going on there. And then debris being pulled up, it's kind of like a superfluidic movement where the debris on the top is actually sucking debris underneath it alongside of it. And then you can see that the heavier stuff falls out. I don't know if we go late enough in time with these, but as it starts losing energy, the larger, heavier debris will start falling out earlier. The lighter debris will continue on later on. So there's a lot of physical effects that go on that I think are just too cool to pass up. And so we have models that we do, that we built that kind of mimic that kind of at a first principles level, and that's what we were using. And so what we go into next is looking at these debris tracks. We're going to use here, for example, this is going to be a 10 kiloton detonation in Oklahoma City. I don't know why I've always liked using Oklahoma City. It's in the middle. I guess nobody would miss it. I don't know. Hey, we just beat them when we get say something. All right, so we have a tool. This is essentially we built this for the Air Force. You've probably heard of what they call the nuclear sniffer plane. They have planes that have gas collectors as well as particulate collectors that will go around looking. It's part of our treaty monitoring that we compare with the IAEA, the CTBTO, and so on. We look around for people doing, for lack of a better word, illegal testing. And so we'll model the cloud array. Sorry, it looks like a potato up there. It's Google Earth only models primitives for shapes, so when you do anything with Google Earth, it looks pretty bad. But we'll model that. That's a little bit more realistic. The cloud rise, the particulate formation, that's all handled in code we have called Delphic. Then we'll pass it on to NOAA's got a very nice long-range transport code called HighSplit. Some of you may or may not have worked with that in the past. We'll pass all the data off to that. HighSplit will do the actual dispersions, and then following the red boxes, we'll show you some of the air concentrations as a function of time based on meteorology. We've also done some climatological studies to look at likelihoods of locations. So if you don't know what the weather's going to be like when the nuke goes off, you can kind of get an idea of where's the most likely place that the fallout's going to go, what places are under most hazard. So upper left at 6 hours, we're just looking at the 2 kilometer slice in the air. So you're not seeing the stuff below or above, about 2 to 3 kilometers. So in the first 6 hours, you can see that there's a fair progression out of Oklahoma City. The orangish gives it kind of a higher concentration, go down to 18 hours, well, 12 hours, and then 18 hours. You can see that the field's getting bigger and bigger, but by definition, that means that it's getting more and more diffuse. So you have a game of how much area is affected versus how bad is that effect in that area. And so that's going to hold track at that 2 kilometer level for this particular.
Does this include all like the altitude changes that happen, especially around like the Appalachian Mountains there?
It does, yeah. So High Split does do terrain modeling as well. A little bit different look, that's that same composite image up there. If we look down at 500 meters, and this probably gets into what you're asking about, you can start seeing a lot more of that lower boundary layer effect in the transport, where you get a lot of Gulf air that kind of comes up there sometimes. Gives you a low level. And then that's just all of them at once. That's just the 12-hour mark, the debris at all the levels. So the lower level where the winds are generally slower is still back there. You can see at the 12-hour point, though, kind of what the debris picture looks like, where receivers might have a problem. So we took a look at this. Starting with that cloud cap, as that rises, it'll eventually get to a point where the energy dissipates away and then it just becomes a transport problem. So looking at kind of that point of maximum rise, we looked at 10 kilotons, 100 kilotons, and 1 megaton. In time of stabilization, you can see obviously the more yield, the longer it's going to take. Those are rough kind of rules of thumbs if you don't have a better number that you can use. And compared trying to pass a signal through that cloud at that time, and you can see the difference compared to clouds, smoke from wildfire, or city hazes and the attenuation levels. The altitude question here is the altitude of the satellite. So the lower the satellite is, the less attenuation, just because there's less distance for the signal to go through. That's why it kind of kneels off at the end there, and that's where the air is the thickest. So it's at that moment in time, if you're unlucky enough to be trying to pass a signal through that particular point, it's very, very difficult. Very unlikely. This thing is still not very big, relatively speaking, at 5 minutes or 30 minutes. But that's our starting point. And so we did a climatological approach, looked at, poor Oklahoma City. We blew them up so many times. So we did like January 1st at midnight, then reran it January 1st at 4 a.m. or 4 hours, and then 8 a.m. and so on. That allows you to catch the diurnal effects of meteorology, spring versus winter. Did that for a year just to get a nice statistical set. Typically with climatology, you'll do it for 5 or 10 years. So you get multiple years in the cycle that lets the statistics stabilize. We're not technically doing climatology on this, we're just getting an estimate and average overall. So this was sufficient for us. And what we're looking here is over these various time intervals, we're going to find the maximum point of interference for each of those 2,000 simulations at each of those times after detonation and build our statistics off of that, just to get a sense. Yes?
Just since you mentioned climate, so now in the last 5 years, there have been, I believe 3 of the last 5 years, we've had heat domes that have gone over Oklahoma City, in particular recently. Do you have a sense of how that would impact things if this were happening, particularly during the summer? So what if everything, when the temperatures in a broad swath were elevated?
That's a good question. I don't have a feel for that in particular. One tangent I'll go on. So I think in general, yeah, I'll take a look up on that one because I don't want to give you a bad answer, but I will give you a different one. Is that high humidity regions, the fireball will tend to rise more because the moisture that gets sucked into the fireball as it cools, you go from vapor to water, you get latent heat release that adds more heat back into the fireball to keep it lofting longer. And you do see, and you'll see this in our models too, you'll see that humidity causes the stabilization height to be higher, which you have to account for if you're using the height for yield estimation. You have to account for the humidity of the area.
So is there a rule of thumb similarly just for atmospheric temperature? Like that? Like there is for humidity?
There probably is, but it's not one I think of. So I want to be sure I don't get, I have a feeling I'm about to get that one backwards. I'm not going to answer without it until I know for sure. But I think you're right, because the difference between the air versus the fireball, and then especially as it entrains the air,
Right.
you know, the colder air is probably going to slow it down faster. But I want to be sure I'm right on that before I give a positive answer. And so what we found is, and we're looking here at, okay, so this is the 1 megaton case. And just looking at those center points of what the maximum debris attenuation is over time. And so the blue is the median, so that's kind of where the statistics fell out, the maximum is up in the red. And so you can see that our peak attenuation early on, very, very high, as you saw in that prior graph. But it falls off very quickly. By the time you get to a few hours, you're down to, you know, the median being, say, 10 at the 3-hour mark. And as time goes on, obviously it goes down further and further. And so it can be a very strong effect, especially for high yield explosions, but it's one that does tend to go away very quickly. And fortunately, like if you're thinking of a stationary ground station, it's one that as it moves, it's over, and then it's not over the station. So it's a very transient effect, even when it is applicable. So there's clouds, megaton, 100 kilotons, and 10 kilotons, and their attenuation at that point of stability right as it rises, but before it just kind of starts dissipating on its own. 1 hour later, you can see just how much it's dropped, and this is a comparison to clouds as well as the uplink and downlink attenuation in clear air. You can see that the uplink and downlink is different. Does anybody want to take a stab as to why they're different?
Does it have to do with, that one makes sense. Never mind.
Okay.
Used to be a thing called the shower curtain effect. It was if your detector is further away from the disturbance when you're shooting up, you get more diffusion before detection. Whereas this was a big topic during the early Star Wars study that APS did.
Yeah, that's it. So in this case, even though there's no debris that we're talking, the atmosphere is thickest closest to the Earth, right? Where the satellite is, they are super, super, super thin. And so when you're sending a signal downward, it's not hitting air until it gets close to the receiver. The other way around, it's hitting it soon, so even just a little bit of perturbation, a little bit of deflection of that photon, it's going to have it has a lot more room for it to move away from the satellite. And so if you account for the not just the absorption of photons by the air, but the deflection of photons, you get a greater amount of attenuation of photons that are missing the satellite, if you will. And so that got us to, this is kind of the final graph in the ground burst study. Has a lot of information on it. The red, the probability of transmission. This line here is just the clear air attenuation. This is at 16 decibels, so this is satellite to ground. And you can see that it takes quite a few photons to get enough to come through. You're still looking at about 4% probability per photon. So for quantum key communication, you have to do this quite often to get enough to go through. And then it goes down to nothing. The estimate of entanglement, I am not a quantum guy, and I will not be able to answer deeply on the questions on this, but this is why we had other people at Oak Ridge do this. The people who know what they're doing looked at this, did some Bayesian estimation on it, and found that the likelihood of that photon remaining entangled through its transport in the atmosphere, even if it transmitted, would go down. And the greater uncertainty is that it's a Bayesian estimate, right? So it's harder and harder to model these because you're losing so much of them that it's hard to develop statistics to get that to line up. And if you look, so for 1 megaton at 30 minutes, that's at that stabilization time. The signal gets impassable if you're trying to go through the cloud. But 1 hour later, when you add it to the clear attenuation, it's bad, but it's significantly better. For 100 kilotons, it goes down almost nothing by the time an hour is done. All told, what we're really trying to say is that if this happens, the debris in the air, that piece in itself is really not something to be concerned with. I mean, if you just had a 1 megaton detonation, this is the least of your concerns, right? But it was nice to kind of go through the rigor, go through the process, and do what was probably fairly intuitive to most people, but at least show that this is realistic according to the models. And so now we're going to look at, that was debris, we'll go ahead and look at redouts. Okay, so now we're going to move upward in the atmosphere just a little bit. Okay, so redout is the, so the fireball, again, it's not in line, but a ways away. The optical radiations coming off of it, the IR, the UV, and all the optical signals that are coming off it, as they go through the atmosphere, those photons are going to be interacting with air, with dust. They're going to be bouncing off the ground and such. And if they go into the field of view, right, they can go up into the receiver as well. And given the sheer volume of photons that are coming off at that point in time, it's not an unrealistic concern. And so that's what we're looking. Okay. And so this was another guy in the group did the studies on it and looked at the black body radiation. And so for the following slide, you see satellites can be at 400 kilometers in Philadelphia, LEO. It's a clear day, so we're not going to be looking too much at, there's no clouds in the air that we're dealing with. We're just going to look at a normal case. And that's some of the satellite transmitter receiver statistics that we need to include. And we'll do this one. So Housatonic is at about 10-mile height burst. I show this one. It's hard to find good ones at high altitude, good videos, but this is one of the better ones. So Livermore did a bunch of film preservations, reconstruction. So if you look at their website on YouTube, they'll have a bunch of these you can find. And you can see that this thing takes quite a long time to expand. And if you're used to seeing ones on the ground, they just kind of go bang and then up. And you can see it's still expanding, still growing. The air is so much thinner, it's just not offering any real resistance to the fire while it's holding its shape a lot longer. And you can see in particular just how bright it is and how persistent this brightness is. And so for these higher elevations, the concept of light coming off and getting into the communications channel does become a more real concern. I think I'll cut it there. Okay, so what we looked at there was for a variety of different heights or different distances from the system itself. How much of it's in the field of view, over a kilometer away, 10 kilometers away or so on. How many photons get into that channel as a function of time. You can see there's a fairly quick drop off as well, but you still get, I mean, if you're close in, you can still get quite a long signal run. And then comparing that to the plot on the right is a little bit more interesting for this. The two wavelengths you see here, the 850 nanometers, those are the mean cross sections. So that's kind of the attenuation rate in the atmosphere for the particles that they're encountering. So if you encounter, like you get down into these small, very small aerosols into almost the molecular level, you get more of a Rayleigh scattering effect. And then you get into this kind of oscillatory behavior. That's what it's called Meade scattering, where it's like resonance cross sections in nuclear physics to a certain degree, where the particle size and the wavelength of the photon kind of interact with each other, and so you kind of get a resonance scattering that occurs as well. And then once that levels out, you get into the more geometric scattering effects. And so you can see that. But the big thing here is to note kind of where it's most sensitive, right? Those higher cross sections mean it's more likely to be scattered. But for these different types of environments, urban, marine, remote, or desert, most of your aerosols in the air tend to be at a much smaller wavelength, so we tend to be down in this range. The reason for checking this was we looked at the clear air case. How much more effect does do the aerosols, does the dirt or smog in the air affect it? And what we found by this is the actual dominant mechanism of the ground for that much light does make a pretty good reflector in the long run. And it points it back in the right direction, gets it going into the satellite's field of view. And then you have that time effect that we talked about. So, but we're still looking at really 30 seconds, maybe a minute for some worst cases. A very transient effect, but a very powerful one while it lasts. And then probably the most fun ones are the high altitude ones. So we'll handle both of these little bars here, starting with the bottom one. Okay, so high altitude definition, starfish prime. If you ever want to fall down a Wikipedia rabbit hole and kind of go down your road, this is the one to do. This is one of the most fascinating tests I think have ever been done. So 1.4 megatons, 250 miles high to burst. And that's the definition of high altitude. And there's this date, July 9th, 1962, 11 p.m. Keep that date in mind. And you can see, as it went off, you can see 900 miles away. Look how bright and big that thing is from 900 miles. And then this is 3 minutes later. Now, you'll notice that it's kind of feathering, I guess, for lack of a better way of putting it. It's not holding, in 3 minutes, not really holding that fireball shape proper, but it's starting to stretch and kind of distort. Does anybody have a thought as to what's going on?
Is that just wind blowing around?
Not 250 miles.
It's probably solar wind. Solar wind protons.
There's probably an effect in that. There's another effect that's going on.
Magnetic field.
Magnetic field. It's starting to create an artificial Van Allen belt. You're seeing the electrons follow the magnetic lines of the Earth. Right? Electrically charged particles moving through a magnetic field. You're going to get a distorted motion. And that's what you're seeing.
How big are those features?
We'll get a picture in a second. So, there we go. Yeah, so some of the effects that happened off this shot, and this was a learning lesson for a lot of people. Obviously, in Hawaii, 900 miles away, right? Phone lines went out, street lights went out, just the charge load that hit the power lines basically started knocking things out. Bunch of satellites taken out, and the creation of what we call artificial Van Allen belts. We'll get to that in a second. But I'm going to back up to that satellites being disabled. What day was Telstar 1 launched?
Wasn't much before that.
It wasn't at all before that. July 10th.
Huh.
It was launched the day after this test, and that persisted in the air long enough to disable it.
What was the average, always perigene apogee for Telstar? Did it actually go
You
through
would ask me
that?
that, I can't
Would
remember.
that be bad?
I thought we heard signals from Telstar, but did it really do?
It took it some time.
Okay.
It didn't immediately disable it, but the radiation did eventually damage it enough that it was rendered inoperable.
And at that point, it's all betas. I mean,
Right.
it's all just betas.
I mean, the protons are there too, right, or the fission products, but because they're so much heavier, they're moving much more slowly. So they don't really add to the effect. It's more the speed of the charge that's causing the problem than anything else.
What was Telstar?
Telstar was the world's very first really public communications satellite. AT&T launched it.
I mean, but really, it has to be just betas from the fission fragments. I mean, a whole day later, I'm assuming even the most energetic fission fragments stop.
Yes, yeah, it's the betas that are the problem. It's worth mentioning the fission products to say why they're not a problem. Yeah, exactly.
And to show my age, I was in junior high school, there was actually a pre-Beatles, we wouldn't even call it rock, but it was a song on radio, popular song called Telstar on radio. So,
Oh, okay.
which you can go to YouTube and hear. Nowadays, it's cringingly embarrassing, but what?
An instrumental.
It was an instrumental, yes. Go ahead. Take a look at it.
Okay. So where we at? Okay, so now what we're going to look at is kind of that kind of get into more of the physics on that ionospheric effect. So electron density in the atmosphere, it follows a day-night cycle. The black line is the nighttime and the daytime there, and that's the effect of solar radiation coming and going. And we'll get into a bunch of these diagrams here in just a second. You'll notice here we're starting at about 25 kilometers, and you're looking at the electron density after the detonation. But we'll get into those here in just a little bit. Okay, so what we're looking at, again, this is that ionospheric effect we want to look at. So we're going to try passing some photons at different wavelengths, 1 centimeter to 100 meters. And we're going to look at the deflection of those photons because of that ionizing or the ionized radiation. Long story short of what that slide's trying to say. So electron recombination, obviously you have electrons, you also have positive particles. They will eventually recombine. In lower atmosphere, like near surface or up to a few miles, the air is so thick that that recombination happens pretty quickly. That's why we don't really talk about this effect too much for the lower levels. But as you get into these very, very high altitudes, they fly so far apart, it can take a very, very long time for recombination to fully occur. And that's kind of what we're looking at here. This is the particle attachment, so this is the recombination rate, basically, shown as a
That's
coefficient.
20 orders of magnitude, am I reading that right?
Yes. Yeah.
Wow. Much atmosphere.
So, gammas on the left, neutrons on the right. There was something there somewhere. 100 kilotons each. So we have here, we're at 1 mile up. You can see, again, that thicker atmosphere, the distance in miles. You can see how fast you go from 10 to 15 down to 10 to the 5th in terms of the gamma flux itself. So the gammas are getting absorbed by the air. They're getting stopped within a few miles. Same thing with the neutrons getting absorbed pretty quickly. If you go into just up to 25 miles, you'll see that the distance, and apologies on miles to kilometers, I hope you can kind of estimate that. These are unfortunately not my slides. Also, apologies for the scale changing on you just a little bit, but you should be at least appreciate the effect that's going on here. Gammas and neutrons are traveling a lot farther. This gives a much greater range to cause this ionization problem that we're looking at. We'll get into the streaming electrons later. So creating the electron generation rate from from the propagation, both the neutrons and the gammas. You can see from a 5 kilometer height of burst, that's the immediate effect of propagation. If you go down to 15 seconds, 60 to 80, you can see the center point where the fireball is kind of rising. And as you have continued decay and continued effects, you see the electron generation rate, one, decreasing quite a bit, but also kind of expanding in scope. And you also see it expanding particularly in upward and outward direction where the air is there. And it's partly that it's generating it, there's also partly that they're not being lost. It's kind of a misnomer figure. You get a neat little effect as you go higher up, so there's 25 kilometers, and you can see the same thing, the same time frames. You get this, it's kind of called a pancaking effect at the bottom, where that thicker air is kind of tamping things down and causing it to slow down and not let it run away on you. And you can see it even more at a 75 kilometer height of burst, where you get this odd effect where obviously right at the burst point you have a very high generation rate, but you also get, as it travels down and then finds that thicker air, you get an increase in the generation rate at that level as well. But again, going back to the ionization, that little bottom part of that chart we're trying to explain, we look at these signals, and if you pass the photons through on this particular trajectory, you just kind of hit that 10 to the 5th mark there. You'll notice that the 100-meter ones, so you're talking like radio wavelengths or something like that, those deflect quite largely. But as you get shorter and shorter wavelengths, you get much, much less deflection of those photons. So even though there's this very high ionization in the air, very, very short wavelengths become very insensitive to it overall. It's one of the benefits of optical wavelength communication. It's a little bit less reflectable, if you will. And remember, we're talking 800 nanometer and 50 nanometer wavelengths, and the shortest I'm showing you here is 1 centimeter. And so the photons themselves are very, very insensitive to this particular effect. Do it for, again, there's the 25 kilometer height of burst, same thing. I mean, the physics should say it's pretty much the same. So you don't see a difference there. 75 kilometers, you just have so much more room now that if you're running your photons through, that you do begin to see more and more deflection. But even so, the short wavelengths are very insensitive to it. Okay, and that's why that bottom bar was empty. It's because those particular wavelengths just don't really see the effect, which was good. Now we have something kind of solid to point to on there. And so this is getting into, I think, what we're talking about a second ago, so that you can see the outer Van Allen belt, as well as closer to the Earth there, the inner Van Allen belt. They're following the magnetic lines. The lines that are coming off at more temperate latitudes stay closer to the Earth. Think every bar magnet with its magnetic lines that you've ever seen. It's the same exact thing. You can see some of the satellite trajectories there as well. And so if you have a higher burst point, it'll tend to fill more of an outer band. If you have a lower latitude burst point, it'll tend to fill a lower band. So if you look at the energies of the betas and free protons in these Van Allen belts, what you'll notice is that in the outer belt, right, it says there it's higher, but the inner belt's got kind of higher energy to it. So if you look at these different orbit heights, those are kind of the energy distributions of the electrons and protons that those particular satellites may be receiving. Which leads into damage to the detector itself. So what we did is we just modeled, and you got to be careful modeling satellites because it's very proprietary, pull a lot of sensitivities on it. So we just said, okay, here's our sodium iodide crystal orbiting the Earth. Very simple model, but it gets what we need to get. As the electrons or protons hit it, they will eventually cause damage to that crystalline structure. That damage will, over time, cause an increase in what's called our count rate, which is basically background noise within the detector. And so a lot of, especially space detector science, goes into minimizing this or making the detectors last as long as they can, because they're kind of hard to replace. Does that just go backwards on me? I just hit the same slide twice. Okay. So, so you can see kind of that rate of dark increases and the damage to the detectors themselves over time, over the course of months, occur. And we talked about this, I think we were talking about it earlier. You can see this a little bit better here. The beta particles tend to spiral around the magnetic flux lines, if you will, and kind of bounce around back and forth until they wear out. But this can take, as you can see here, this is really what we're trying to get to in this particular question, is how long does it take? So in the high altitude, the GEO, it does dissipate fairly quick. I think you lose a lot of electrons to free space over time. But those LEO orbits, right, if you get artificial Van Allen belts built up there, it can take quite a few months for those artificial Van Allen belts to finally dissipate and calm down. So during this entire time, when you're up 10 to the 8, 10 minus 9 particles per square centimeter second, if you kind of go back here, you can see that at those higher, not there, that's count rate. But yeah, so that's where the LEO has that kind of higher line to it. The NEO, I forget why that's higher. I'll get back to you on that. But you can get the idea, though, that as you have these electrons, it just takes a very, very long time for them to go away, which means you have this persistent damage occurring to your detector over time. Yes?
Do you get a lot of noise from the light created by the electrons moving along the field lines? Like they're oscillating, you say, right? So they should be generating some light.
I believe, isn't that a large part of the auroras?
Yeah, it is, but what
Yeah.
in your detector on your satellite, is that not increasing the noise to that, or it's not really, is it negligible?
The light, we didn't evaluate that. Yeah, we looked at the direct electron damage.
Okay.
But you're right, that is an interesting question.
Because you thought about the reflected, right? The reflected light in the previous example, I thought that would be creating light too, so maybe it was.
It should, but I don't have the answer for you on that. It would depend obviously on how intense that light is relative to
Signal.
the light in that redout condition we were looking at before. Yes.
So the dissipation of the Van Allen belts happens because of the recombination of the electrons into some molecules, right, atoms?
Mhm.
What atoms are there out there for, it's not a lot of atoms out there.
Right, so in the geo case, one is just that it's a lot more volume on that magnetic belt, so they spread out so that the density in one particular location goes down, partly as a volume gain. I think you also get more loss to free space, where they'll eventually spin off as well, so you get a different kind of dissipation.
So it's the radiation itself is subdominant in terms of the energy loss of the electrons? In principle, things like this.
Yeah, as it's spinning off photons, it's going to be
Yeah.
losing energy over time.
But is that a major or minor effect in the dissipation of the?
I'm unfortunately not the right person to answer that question for you. But that is a good question. Yes?
I mean, the neutrons have on this week a shorter persistence period, no matter what they eventually decay. But do you see activation signatures in detectors for this as well?
From neutrons?
Yeah,
Free neutrons?
well, they're,
Well, you would have free neutrons from a detonation for a short while.
yeah.
I mean,
I don't know, it's a good question, I don't
You
know.
could even get some of the high energy electrons that you had there are high enough
Right.
that you could do gamma in.
I've not heard of that, it's an interesting question, but I do not know the answer.
I mean, how many nuclear detonations have been detected via satellites?
How many have been detected by satellite, or how many have been at the altitudes of satellites? It's a different question. Because we have the satellites that detect nuclear detonations on the ground, but they do it by the optical signal.
It blows up in orbit, we know it's,
Right.
we notice.
Yeah, when they're very high altitude, it's impossible to miss. I think that gets us to this one last time. So hopefully this makes a little bit more sense now. This is about persistence, right? So the artificial belts can last for up to months. The debris, even though the effect is very localized and transient when it occurs, when the effect occurs, it's on the order of minutes to hours that it's of a concern. Redout is more of a seconds to minutes. It can be a quite strong effect when it occurs. And so you might lose a station or a satellite's ability to communicate for a while, but it will, obviously, as the fireball cools, it's going to go away. But the ionization question, just at these wavelengths, if we were talking radar or radio wavelengths, completely different story, but at these wavelengths, it's not very much of a concern. That's why they had radio blackouts after the Starfish Prime for quite some time. And that is my last slide. And managed not to go over.
A few minutes for more questions.
Yes.
Do you know what DoD is doing to make our satellites more resilient to these effects, or any sort of defense measures?
Yeah, generally it's in the design, like red hard electronics, if you've heard that phrase before, looking at materials that are more robust against radiation and so on. I'm not in the satellite space, so I don't have like detailed answers for you on that. But that is a very, DoD is working on it, NASA's working on it in a very large way. private company to send these things up. Everybody is very highly interested in this. Yes?
Just to add to that, just this past weekend, we did testing with Missile Defense Agency of the Hill to determine electronic coordinates for developing a target specifically for that purpose, just to reinforce what you were saying.
Right.
That's a very hot item right now.
It is, and as we increase the number of satellites, it's only going to be more and more important.
This wouldn't be like radiation hardening wouldn't, yeah, never mind.
Do you have a question?
Why did you choose Oklahoma City for this simulation, and why is it representative of these?
I've done Oklahoma City in the past for things like this. It's nice in that no matter which way the wind blows, you're over land for a while. So we did, so going back to what we talked about with the climatological studies, we did a 15-year climo study on Oklahoma City to see if somebody lit off a nuke in Oklahoma City, and you can kind of know, like you know which way the winds tend to go, like how severe, how far things go. Part of that it was looking at, so there's kind of two sensor systems. One is the International Monitoring System, one is EPA's RADNET system that do detect, or ground stations that detect, this is completely off topic, but let's go here. They'll detect radiation for different purposes. And so we wanted to ask if you had a nuke go off, would one of those locations be able to collect enough debris for forensics analysis? And can we get a free target of opportunity where an air volume sensor is sucking in so much volume it actually concentrates the debris, gives you a bigger, better sample that you can do more analysis on. And so we wanted to evaluate some of those existing networks. And so Oklahoma City became one of the ones I used for that, just because if it's over water, you don't have a ground station. Right? And so I just did it all over again here. It had nothing to do with the game last weekend. Yes?
I just had a question about the models that you were using when you're doing your high altitude nuclear explosion tests.
Yes.
Obviously, when they did the starfish test, they didn't expect the longevity and the way that things did perform, but how have you now adjusted your models to try and take account of what you did? Is it from the observations?
It's a bit of stitching. As you can obviously tell, modeling these things can be tricky at times, especially for this particular work. We had to keep it very non-sensitive, very open, and we published quite a bit on this. So it was mostly like ComSol for create the fireball, add in just some reactor fission products, and then do some estimates on the electron generation rate and so on. That falls out of that. So we didn't actually model the weapon itself. So these are not true numbers in that sense, but they're good enough to get the feel of the effect, to get an estimate of what's the biggest problem and what's not a problem. And that's what we were after. Yes? Oh, sorry.
Did your 15-year climate models for Oklahoma City, did those also include nearby precipitation at different times of year and how that affected cloud travel or?
Yes and no. So that gets into the Met Transport Code itself, and HISPLIT can do that. For some of the climate we did, we left that off because precipitation significantly increases over time. For some of the studies we did, for 15 years, I think we had it left turned off. Now, the wind effects would have been there from storms going through, like the vertical and the turbulence and the shear effects would have been there. But the actual washout from the would not have on that. But we did some 5 and 10 years that would have included it.
You had a slide earlier about internal dosimetry. I was just wondering if this is connected to this project, or it's a totally different place around.
This?
Yeah.
So what I presented was completely uncoupled from that. We did absolutely nothing regarding health effects on it. I put this in there as a part of explaining what my group was, and partly on my connection of why I was even here in the first place. So, and to advertise the fantastic work that you all are doing.
I was wondering that if there are astronauts in the space station, and then it might be...
Yeah, so no, the dosimetry to astronauts is a big deal. Dosimetry to astronauts is generally external dosimetry, and these projects are internal dosimetry. But that is it's a fascinating field because it's not just betas and gammas, protons, right? You get all the muons and all the cosmic radiation, the exotic stuff you don't see on Earth. So it's a very interesting field of study. Yes?
I'm just curious if the debris from Fukushima accident had any effects on the communication with satellites.
Not that I know of. That's because it's much slower release over time, right? So the actual amount at any one location in the air is going to be so much lower that it's going to be below aerosol levels.
That rule of yours, 1 kiloton per kiloton?
Oh, yes, yeah, I'm sorry. I
I saw that up there, I just wanted to, is that something we should always keep in mind?
Yeah, and that's out of...
A ground burst? I'm sorry, what was that?
There we go.
Yeah.
Okay, so yeah, if the burst on the surface,
Yeah.
and this is based largely out of our
Surface.
tests in Nevada, a surface burst, yeah.
Yes.
That 1 kiloton of nuclear yield will loft 1 metric kiloton
Right.
of soil up into the air. That's the rule of thumb out of Lassendall's effects of nuclear weapons.
Cool.
I brought 2 copies I'm going to leave with your department, so you can enjoy those later on. That is a joint Department of Energy, Department of Defense handbook that was written originally in 1977. It's one of the absolute gold standards for reading more about effects, right? It's not the actual performance of weapons or anything like that, so it doesn't go into that realm, but things like the health effects is Follis chapter 9, there are health effects chapters in there. There's things on shock waves and the ionizing radiation and so on.
It's also available online.
Yeah.
It is available online.
Interestingly, if you put that in, I think, to answer my question about the heat dome effects, 10 degrees centigrade is several tenths of a percent of a kiloton in a kilogram. In a kiloton. So it's actually measurable. So it basically would be like if the bomb had more energy, because the debris that it's got has got more thermal energy going up initially.
Yeah, and my suspicion, to give you my suspicion on that I just need to verify, is that if the air is warmer, the fireball is losing its heat more slowly.
Right.
And so it's going to keep a lower density for a while and continue to decline longer.
Right.
Whereas colder air, it'll cool off faster, especially the entrainment, the air getting pulled into the fireball from underneath is going to cool down much quicker.
And it seems to matter a lot, like the specific heat of soil seems to matter with water content a lot.
It does,
It's
it
like
does.
We're factors of 3 or 4.
Yeah, that's where we're kind of cursed. I'm going way too long. I feel like I'm going to get the shepherd's crook.
Sorry.
That can be good, more questions.
But I'll finish this one, yeah. So it's one of the curses in this field. We did all our testing in the desert or out in the ocean, right? So we have basically all water or all sand, and not really a whole lot in between. There's a few other cases. Well, we did some that had like a bunch of coral material holding it, and that's very fascinating. It's a very different debris. I almost did a talk entirely just on the dirt, but I felt this would be probably a little bit more interesting.
Are you able to use any of the Soviets' data because they did test conditions under other conditions?
Yeah, they've released some. So you can use that. And there's also the British tests in Australia, and also desert too, but it's just different soil phenomenology.
All right, I think we're gonna move on to the career conversation, but before that, let's thank